All right, 3.4 part 2. Using second derivative test, find the relative extrema for this function. So we usually would find our relative extrema by taking our first derivative and finding out when that is 0 and undefined to get those critical values and do the first derivative number line. Now remember, we should always talk about the domain first. This domain would be all real numbers. Okay, this is a simple polynomial equation. The first derivative, I would go ahead and factor out my negative 15x squared. And then that leaves me right here with a difference of squares of 1 minus x and 1 plus x. So my critical values would be x equals 0, x equals 1, and x equals negative 1. So for my first derivative number line, I would have had those three values. I'm going to make a little graph of that real quick. So negative 1, 0, and 1. Again, this would be the first derivative number line test. That first derivative would be an x to the fourth graph, which we know ends going down and down. And at x equals 0 would be tangent and come back up and back down. So I'll show you what that would look like. So again, this is the picture of the first derivative. So this is the first derivative. The reason I know it's tangent at x equals 0, because that was the multiplicity of 2. Whenever the multiplicity is an even number, it's going to touch it and turn around. So we have x equals 1, we have x equals negative 1. Those are each multiplicity of 1, so it must cross through it. But x equals squared would be a multiplicity of 2, which is even. So again, any even multiplicities is going to touch the graph and turn back around. And that original was an x to the fourth, but a negative coefficient. So it was a down and down. So my first derivative number line test, this now gives me values of negative, positive, positive, and negative. So from the first derivative, I believe I already have a minimum at x equals negative 1, and then I have a maximum at x equals 1. Because this is telling me my graph is decreasing and then increasing, so that'd be a minimum. If my graph goes from increasing to decreasing, then this would be a maximum at 1. So again, on the original function of f, that's what's happening. All right, now let's go ahead and take a look at that second derivative. So I'm going to factor out a 30x here. That would give me a fake critical number of x equals 0. From this one, I would get negative 1 divided by negative 2, so 1/2 plus or minus the square root of that. And that would give you those secondary critical numbers if we were looking for concavity. But we're supposed to be using the second derivative to find out if this graph is a maximum or minimum at x equals negative 1, 0, or 1. So what we need to remember is that if a graph is concave up, or if a graph is concave down, what happens with those graphs? See, if a graph is concave up and you have a critical value there, then you would know that this would be a minimum. If a graph is concave down and that happens to be a critical value, then you would know that that's a maximum. So what happened in the first part, we found the critical numbers of negative 1, 0, and 1. So in the second derivative, we would find out that if x is negative 1 in the second derivative, this would be a positive number. Therefore, if that's a positive number, that part of the graph where x is negative 1 would be concave up. So therefore, at x equals negative 1 would be a minimum value. The second derivative at 0 was 0. So there's not going to be a max or a min at 0. The second derivative at positive 1 was a negative. So again, at positive 1, since the second derivative was negative, that means that part of the graph is concave down. And since 1 was a critical value, that would make a maximum happening there. That ends your lesson for 3.4. That last slide, when they use the second derivative to determine the maximum minimums, I wanted to show you that just in case there's a question on the final exam with that. I tend to just use my first derivative test and the number line test for maximum and minimums. I personally don't prefer the second derivative test for max or min for relative extrema. But I hope you understood that. If you didn't, just ask me about it and I'll re-clarify that. So remember, for concavity, you have to take a second derivative. Once it's 0 or undefined, make sure they exist in the domain. Make your number line with those fake critical numbers. Notice I even spent secondary critical numbers. If that value is positive, it's concave up, and if it's negative, it's concave down. Okay, to find those points of inflections, you would have to find that second derivative. And again, it has to change concavity for it to become an inflection point. If it stays concave up and it doesn't change what it is, then it's not going to be an inflection point. Okay, guys, good luck to you. See you tomorrow.